Dear students, in first year PUC, we have learnt a chapter called gravitation. When there is a body of mass m, it produces a field around it, and this field is called a gravitational field. In that field, if I place another mass m, it experiences a gravitational force which is attractive. At the same time, that mass possesses an energy, and this energy is called gravitational potential energy. In a similar manner, if I consider a charge q, either positive or negative, it produces a field around it, and that field is called electric field. In that electric field, if I place another charge called q0, so this is a charge which produces the field, so that's why this is a source of electric field. This charge is called the test charge. Now this test charge, it experiences force, and this force is called electrostatic force. At the same time, this charge possesses energy, and that energy is called electric potential energy. So how to calculate the electric potential energy in this particular charge? So electric potential energy is given by, we use the symbol used for that, is given by electric potential at that point due to Q. Electric potential at that point due to this charge into the charge. So this is how we can calculate. So how do you find the potential energy in that particular charge? So U is equal to, what is the electric potential at this point, which is at a distance r? That is 1 by 4 pi epsilon naught Q by r into this Q naught. So this is how you can find electric potential energy at any point due to any number of charges. Now what if the sources charges are many? Let me consider if there are system of charges Q1, Q2, Q3, that is. And then if you want to find the potential energy stored in that charge Q0, then we use the same formula. U is equal to, now we have to find the electric potential due to system of charges. I'm going to write this as a V net or V total. Total potential at that point into the charge. This is how one can measure the electric potential energy stored in a charge at a particular point. And this is similar to the concept that we have learned in the first year, where we measure gravitational potential energy stored in a mass due to a single mass or due to system of other masses. If I consider a system of charges like this, Q1, Q2, and Q3 like this, there are system of charges, many. Now you can see every charge is present in an electric field produced by the other charges. For example, at this particular point, there is a field due to Q2, Q3 as well as Q4. At the same time, at this particular point, there is an electric field due to Q1, Q2, Q3. That means every charge is present in an electric field produced by the other charges, due to which every charge possesses energy. So what is the total energy stored in the system of charges? So that is what I'm going to explain next. So I'm going to start with electric potential energy. Electric potential energy in system of two charges, and the condition is in the absence of external electric field. So we are going to find electric potential energy in a system of two charges in the absence of electric field. So let me consider two charges, Q1 and Q2, and they are separated by a distance r. And I want to find what is the energy stored in the system of two charges, because Q1 is present in an electric field produced by Q2. At the same time, Q2 is present in an electric field produced by Q1. Now, how do we measure energy? So, energy is always a measure of the net work done. So, in this case, if I have to measure the energy stored in the system of charges, I have to measure the total work done in moving the charges from infinity to their respective position. So, total energy stored in the system of these two charges is a measure of, or is equal to, total work done in moving the charges from infinity. Now, why there is a need to move these charges from infinity? Because at infinity, there is no field, there is no energy, therefore, the zero energy level is nothing but infinity. So, that's why we move the charges from infinity to their respective position. So, let's measure these, move these charges from infinity to this position, and then we'll measure the work done, and that gives the total energy stored in the system of two charges. So I'm going to consider for reference, so this is the zero energy level, okay? So where we have the two charges, Q1 and Q2. So let's assume that, it's a zero energy level. And I want to shift those two charges to these 2 points, point A and point B. So I'm going to first move the charge Q1 from infinity to the point A. Now when we move this charge Q1, as you can see, this is a free space where we don't have any other charges, there is no field. Therefore, what is the work done in moving the first charge? So work done is equal to the charge moved into the net potential. But since there is no field, there is no potential, therefore that potential is zero, therefore the work done in moving the first charge is zero. Now we have moved the first charge and we have not done any work as there is no field here. So we have shifted Q1 from infinity. Now I'm going to move the second charge, and when I move the second charge, as you can see, there exists a charge Q1 and which produces the field. Therefore, there is field all over till infinity, and because of that field, at this particular point, there is potential, and let that potential be V at a distance R. And we can measure that potential. And that potential is given by 1 by 4 pi epsilon naught Q1 by R. So let's measure the work done in moving the charge Q2 against the field produced by Q1. So the work done in moving the second charge is the charge moved into potential at that point due to Q1. That's equal to Q2 into potential is given by 1 by 4 pi epsilon naught into Q1 by R. So what is the net work done in moving both the charges? It's W1 plus W2. And when we add these two, we get 1 by 4 pi epsilon naught Q1 into Q2, Q1 Q2 by R. And we know that work done in moving both the charges is stored as electric potential energy in the system of charges. So U is equal to 1 by 4 pi epsilon naught Q1 into Q2 by R, because this W itself is equal to U. So this is the expression for energy stored in the system of two charges, and most important, in the absence of any external field. So the product of the charges divided by the distance into that constant will give you the energy stored in the system of these two charges. Now, when we know the energy U, 1 by 4 pi epsilon Q1 into Q2 by R, we can always calculate the force if I know the electric potential energy. So we can calculate like this. So we know that electric field and potential relation is E is equal to minus dV by dx. That is, electric field is always negative potential gradient. You multiply by charge Q naught here and then minus Q naught into dV by dx. And that is minus d by dx of, if I multiply V into Q naught, V into Q naught. And that gives this product, potential into the charge gives energy. And Q naught into E here is nothing but F, which is the force. So F is equal to minus du by dx. Electric field is always a measure of or equal to negative potential gradient, whereas electric force is equal to negative potential energy gradient. So these two equations are important, and you have to remember from all the exam point of view. So if you know the potential energy, it is very easy to calculate the force. What you need to do is you have to find the negative potential energy gradient. That is nothing but differentiating potential energy with respect to x. And when I have written this equation, I am writing that with the assumption that u is a function of x. If u is a function of r, then you have to write minus du by dr. If u is a function of y, then we have to write minus du by dy. Okay. And we can prove this equation with the help of this. So, refer the equation. U is equal to 1 by 4 pi epsilon naught Q1 into Q2 by R. Let's measure du by dr. Du by dr. That is differentiating U with respect to R. 1 by 4 pi epsilon naught into Q1, Q2 by differentiation of 1 by R is minus 1 by R square. It's R square minus, which I'll write here, minus 1 by R square. And now if you look at this equation, 1 by 4 pi epsilon naught Q1 into Q2 by R square, you are very much familiar with this. This is nothing but equation for force. From Coulomb's inverse square law, we get this equation, 1 by 4 pi epsilon naught into Q1, Q2, therefore this is equal to minus F. So therefore what we have proved here is F is equal to minus du by dr. That is, the electrostatic force is always equal to the negative electrostatic potential energy gradient. So find the differentiation or derivative, you will get the expression for the force. Now whatever the energy that we have found just now is a system of two charges in the absence of external electric field. Now what if in the presence of external field, what is the expression for the energy stored in the system of two charges? So let us consider a uniform electric field of magnitude u directed as shown in the diagram. And here I am going to consider 2 points A and B, where I want to bring two charges Q1 and Q2, and I want to find the total energy stored in the system of two charges. Now first, as a reference, again I'm going to consider that zero energy level, which is infinity, in which I'm going to consider two charges Q1 and Q2. So first, when I bring first charge Q1, as you can see, there exists an electric field E. And at these 2 points, let V1 and V2 be the electric potential at these 2 points. When I bring first charge Q1 to this point A, we are moving Q1 to A. So there exists a potential. The work done in moving the first charge W1 is equal to charge moved into the potential at that point. It's a V1. This time work done in moving the first charge is not zero because of the presence of the external field. Now what is the work done in moving the second charge due to this field which is there, which we have applied, that's E. That is charge moved into the potential at that point, which is V2. So this is the work done in moving the second charge against this field. But we know at this particular point, there exists another field produced by the charge Q1, which we have brought here. So therefore, how to find the work done in moving the second charge Q2 to point B against the field produced by Q1, which we have already calculated in our earlier discussion. So I'm going to write that equation straight away, which is 1 by 4 pi epsilon naught Q1 Q2 by R. So let me repeat what I have explained. So first, W1 is the work done in moving the first charge against the existing field E. W2 is the work done in moving the second charge Q2 against the same field E. And this W3 is the work done in moving the second charge against the field which is produced by the charge Q1. And when we add all this, we get the net work done in moving both the charges. So W is equal to W1 plus W2 plus W3, that gives the net field. So net work done. So W1 is Q1 V1 plus Q2 V2 plus W3 is 1 by 4 pi epsilon naught Q1 Q2 by R, Q1 Q2 by R. So this is the net work done. And this net work done is stored as electric potential energy in the system of two charges. That's why this W itself is equal to U, that's Q1 V1 plus Q2 V2 plus 1 by 4 pi epsilon naught into Q1 into Q2 by R gives the net potential energy stored in the system of two charges in the presence of external electric field. So these two terms are additional because of the presence of the two field, this field, extra field. If this field is 0, then these two terms becomes 0 and you'll get the expression for 1 by 4 pi epsilon naught Q1 into Q2 by R. So whatever that I've explained here is the energy stored, electric potential energy stored in the system of two charges in the presence of the field. That was the first case. And what I have explained now is the electric potential energy stored in the system of two charges in the absence of the electric field. Sorry, this is in the presence of the electric field, and earlier I had explained in the absence of electric field. Now, what if there are more charges? So, I'm going to consider now system of three charges. Electric potential energy in the system of three charges. Electric potential energy in the system of three charges. So the method remains the same. We have to consider three charges, Q1, Q2, Q3, and I'm going to consider them at the zero energy level, reference level, which is infinity. So Q1, Q2, Q3. And we are going to move each charges, Q1 first, and then Q2, and then Q3. And then we calculate what is the work done in moving each charges, and then we are going to add all the three works. That gives the total electric potential energy stored in the system of the three charges. And we are going to place them at 3 points A, B, and then C randomly. That can be taken along the straight line, or it can be taken anywhere else, C. So at A I'm going to place Q1, at B I'm going to place Q2, and at C I'm going to place Q3, so that these points are separated by distance. R12 is the separation between A and B, and R23 is the separation between B and C, and R31 is the separation between A and C. So what is the work done in moving the first charge? When we move first charge, we don't find any charges here. So the electric field is 0, electric potential is 0. That's why work done in moving the first charge is 0, as there is no charges, there is no potential, there is no field. Now Q1 is shifted from infinity to this location. Now when I move second charge, we find there exists a charge Q1 which we have shifted, and there is a field. So work done in moving Q2 to the point B is given by W2 is equal to the charge moved into the potential at the point B. And the potential at that point B is only due to this charge Q1. So that's why it is Q2 into 1 by 4 pi epsilon naught into the charge, which is Q1, by the distance between A and B is R12. So this is the work done in moving the second charge. And when we move the third charge to the point C, there exist two charges now, Q1 and Q2. Therefore, what is the work done in moving the third charge? Work done in moving the third charge is W3 is equal to the charge moved, which is Q3, into the total potential at this point C. Why total potential? Because there are two charges, and at this particular point there is a field due to Q1, there is a field due to Q2. That's why there will be net field and net potential which we can measure. And that is given by Q3, that is this. And how to calculate the net potential? Constant 1 by 4 pi epsilon naught into the first charge, which is Q1, by its distance to the point C is R31, plus the second charge, which is Q2, by distance R23. So these are the work done in moving first charge, second and the third charge. So we are going to find the net work done by adding all these three equations. So W1 is 0, W2 is 1 by 4 pi epsilon naught, Q1 Q2, Q1 into Q2 by R12, plus 1 by 4 pi epsilon naught into Q1 Q3, Q1 Q3 by R31, and plus Q2 Q3 by R23. So as you can see, for both the terms 1 by 4 pi epsilon naught is common. So therefore W is equal to 1 by 4 pi epsilon naught, which is common, into the first term is this Q1 Q2, Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R31. And this work done, total work done in moving all the three charges, is stored as electric potential energy in the system. So the final expression is U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R31. So this expression for electric potential energy stored in the system of 3 charges. So let me write all those equations, a list, so that you can revise them. I started with energy stored. So this is the first equation. Energy stored, electric potential energy stored at a point is given by charge into potential. This is how do we measure the electric potential energy at a point. And if there are many charges, this will be V net or V total. Then energy stored in the system of 2 charges in the absence of external electric field, 1 by 4 pi epsilon naught Q1 Q2 by R. With this, you can always calculate the force, which is negative potential energy gradient. In the presence of external field, the energy stored in the system of 2 charges is given by Q1 V1 plus Q2 V2 plus 1 by 4 pi epsilon naught Q1 Q2 by R. And the next, energy stored in the system of 3 charges, that is 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R31. So these 5 equations are important and they are all related to electric potential energy stored in a single charge in a system of charges. Now let's solve a numerical based on the topic that I've explained. The statement of the numerical is 2 point charges 2 microcoulomb and minus 5 microcoulomb are separated by 5 centimeter. Find the work done in increasing their distance by 5 centimeter. So the 2 point charges given Q1 and Q2, they are separated by a distance which is R1, and that's given 5 centimeter. So we have to find what is the work done in separating them, increasing their distance by 5 centimeter. That means now the same 2 charges are shifted by another 5 centimeter. So that is R2 is 10 centimeter. Now what is the need to do the work in shifting them? If you look at the nature of the charges, first charge is a positive, it's plus 2 microcoulomb, and the other is minus 5 microcoulomb. So what is the nature of the force between them? It's attractive, they tend to move towards. So if you want to shift them by further, or if you want to increase their distance, you have to exert the force and you have to do the work in moving them or in taking them away. And that work we have to calculate. So as we know, according to the work energy theorem, work done here in this case is always a measure of the change in the energy of the system. So when 2 charges are there separated by a certain distance, we can always calculate the potential energy stored in the system of charges. That's U1 is equal to 1 by 4 pi epsilon naught, product of the charges and then the separation. When they are further increased by 5 centimeter, we can again calculate what is the new energy stored in the system. That is U2 is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R2. So once we know the initial energy and the final energy, and the difference in the energy will definitely give you the work done. So let's calculate the initial energy. 1 by 4 pi epsilon naught. The constant is 9 into 10 to the power 9. Product of the 2 charges, it's a 2 micro. 2 into 10 to the power minus 6 into, we have to consider that minus sign, 5 into 10 to minus 5 into 10 to the power minus 6 divided by separation 5 centimeter, which is 5 into 10 to the power minus 2. So here this 5 will get cancelled and there is a minus sign, and this 9 into 2 will give you 18 into, this gives 9 plus 2 here, 11 and minus 6. So that will be 10 to the power minus 1. And that's same as minus 1.8 joule. Now this is the initial energy. Let us calculate the new energy. That is 1 by 4 pi epsilon naught, 9 into 10 to the power 9, into the product of the charges, which is 2 into 10 to the power minus 6 into minus 5 into 10 to the power minus 6 divided by R1 is 5 centimeter, R2 is 10 into 10 to the power minus 2. So as you can see here, when the distance is double, because the rest of the factors are same, when the distance is double, this energy is half. So we can very easily write, if this is the initial energy, half of it is a minus, it's 0.9 joule is the answer. Now, work done is always a measure of the change in energy. Now, which energy is greater, minus 1.8 joule and minus 0.9 joule? So, basically minus 0.9 joule is greater, therefore it will be U2 minus U1, which is minus 0.9, then minus of minus 1.8, and that gives an answer 0.9 joule. So, this is the work done in shifting the charges by 5 centimeter. So another example, if I take plus 2 microcoulomb and minus 3 microcoulomb separated by a certain distance, and then plus 2 microcoulomb and then plus 3 microcoulomb separated by a certain distance. In the first case, if distance is increased, the distance is increased, what happens to the potential energy? Whether it increases or decreases or remains same. That's what we have to find. And the same question, if distance is increased, what happens to the potential energy? So that's what we need to calculate. Now we know the potential energy equation, U is equal to 1 by 4 pi epsilon naught, product of the charges, and then divided by the separation. Now based on this, it looks like, if distance is increased here, if R is increased, then U should decrease. But that is not the right answer, because we have to consider even the charges as well. So one is positive, other is negative. So therefore this product is negative. And because of this negative sign, as R is increased, U also, it increases. So the answer to this question is increases, and it will not decrease. That is because of the sign of the charges. So as R is increased, U also increases because this product is negative. But in the case of two like charges, it's very easy to answer. U is given by 1 by 4 pi epsilon naught, Q1 into Q2 by R. This product is positive because of the two positive charges. And in this case, when R is increased, U varies inversely as R, so that's why U, it decreases. So therefore, the nature of the charges will decide whether the energy increases or whether energy decreases. The variation is not same, and that is an important point which you have to remember from this equation point of view. So I'd like to give one more example for the system of three charges. So let's consider a system of three charges, Q, Q, and then Q. This angle I'm going to consider 45 degree. And the question is, find the relation between Q and Q for which the total potential energy of the system is 0. So we have system of 3 charges, Q, Q and Q given, and we have to find the relation between Q and Q for which the total potential energy of the system is 0. Now since this angle is 45 degree and if this is 90, this is also 45 degrees. So that means this becomes an right angle isosceles triangle. So let's consider this side as R. If this is R, so this has to be R. If this is R and this is R, by Pythagoras theorem, we'll get this as root 2R. So let's use the potential energy stored in the system of 3 charges, which is U, the constant, 1 by 4 pi epsilon naught, and then Q1, Q2 by R12 plus Q2, Q3 by R23 plus Q3, Q1 by R31. It's given that U is 0. So this is a constant K, let me write, cannot be 0. Now let's consider the product of the charges. So I'm going to consider Q1, Q2 and Q3. You can consider this as Q1 and this as Q2 and this as Q3. So product of the 2 charges Q1, Q2, that will give you Q square by root 2R plus Q2 and Q3 will give you QQ here, Q and Q separated by R plus another similar product Q and Q separated by R, QQ. So since this cannot be 0, this term has to be a 0. That is Q square by root 2R plus 2 such terms, it's a 2QQ by R must be equal to 0. So it's very easy to simplify. Q square by root 2R is equal to minus 2QQ by R. So this term will get cancelled, one of the Q will get cancelled, and that will give you Q is equal to minus 2 root 2Q. So this is the relation between Q and Q for which the total potential energy stored in the system becomes 0. So this is the application of the equation which we have derived earlier.